Hi guys, I'm Brian.
I'm Ethan.
And I'm Xander. Today we'll be talking about the comparison of rigid and compliant tendon dynamics and static optimization of gait analysis. To give some background for our study, we first wanted to challenge the common modeling assumption of a rigid tendon. Reading Kaneda's paper from earlier this year, it seemed she believed modeling tendon compliance was important to accurately predicting improvement in internal joint forces. And we ultimately wanted to learn more about the effect of tendon compliance on simulation results, learning a lot more about the OpenSim API along the way. And now, the research question we finally settled on. How do muscle activations and forces change in walking simulations when comparing rigid versus compliant tendon models? Next, Brian will walk you through an overview of our methods.
So at a high level, we used a walking dataset from a Dembia 2017 paper and compared muscle activations and forces from two different static optimization algorithms. One, which used a rigid tendon model, which we were given from Lab 4, and another, which used a compliant tendon model, which we coded up ourselves. Now, I'll go into detail about how we implemented tendon compliance. This is the familiar setup for static optimization. We have our objective function subject to various constraint equations, and many of these variables in our constraint equations are well defined. After scaling our model, we know the max forces of each muscle. After solving inverse kinematics, we know the muscle moment arms and the muscle tendon unit length. And after solving inverse dynamics, we know the joint moments. However, even though we know the muscle tendon unit length, after solving for inverse kinematics, we don't know how much of that length is taken up by the tendon, since we're allowing it to be stretchy. And so as a result, we don't know the length, velocity, or pronation angle of the muscle. So to solve for muscle length, we use this equation adapted from an Ulrich 2022 paper, which equilibrates tendon and muscle force. This equation uses the current time steps muscle tendon unit length, the previous time steps muscle activation, and importantly, it assumes that the muscle fiber velocity is 0. What we end up with is an equation with one unknown that's set to 0, so we can iteratively solve for muscle length using a root finding algorithm like Newton's method. The reason we assume muscle fiber velocity to be 0 is because if we had allowed it to be an unknown variable, our equilibrate muscle force equation would become a differential equation with no guarantee of convergence when solving. Secondly, it has been shown in Ulrich 2022 that this assumption of 0 muscle velocity in compliant tendon models was comparable because it produced relatively accurate results similar to experimental EMG data. So now, if we go back to our original static optimization setup, our initial unknowns become known after we equilibrate tendon and muscle forces. Now, all our constraint equations are well defined and we can proceed with static optimization using fmin_con. So that was a very quick summary of our implementation of tendon compliance. Next, Ethan is going to talk about the results we got.
These are the results of the time series plots for muscle activations in both the rigid and compliant models. The activations of the rigid model can be seen in blue, and the activations of the compliant can be seen in red. The solid lines represent the right leg, while the dashed lines represent the left leg. Here, we overlay activation plots. We see some muscles where activations are very similar, while other muscles' activations are very different. To get more quantitative results, we calculated root mean squared error between rigid and compliant tendons, and then we reordered them from largest to smallest. To highlight a few muscles, we see medial gastrocnemius had the largest RMSE value, followed by the iliacus and the biceps femoris long head, while other muscles near the foot, like the tibialis posterior, had the lowest. We then wanted to make inferences on why some muscles had high RMSE values, so we plotted them against their normalized tendon slack length. These are the highlighted muscles from earlier. There seems to be a slight positive trend between RMSE and tendon slack length, but we had outliers in the lower right, like the tibialis posterior. Upon investigation, we noticed many of those outlier muscles, like the tibialis posterior, had minimal activation during walking, so we filtered them out. We did a linear regression of the data and found a slight positive correlation between normalized tendon slack length and RMSE in activation between rigid and compliant tendon models in static optimization. Next, Xander will walk through the results of passive forces.
Suspecting that muscle activations weren't telling the whole story, we next investigated the correlation between normalized tendon length and the percent change in passive force between compliant and rigid tendon models. As you can see by all the data points being below 0 on the y-axis, passive force exclusively decreases in the compliant tendon model for all muscles. Further, there is a stronger correlation than we saw for activation of 0.66 between normalized tendon slack length and percent decrease in passive force. This is consistent with our expectation. Since the overall musculotendon unit length is determined by inverse kinematics, which is identical for both models, we expect to see that the muscle length change in rigid tendon models will be greater to compensate for a rigid tendon, leading to higher passive forces. This observation is also supported by previous literature. Millard's paper from 2013 shows a similar trend in increased force error for muscles with longer relative tendon length. Our regression line ends at roughly 60% error for normalized tendon length of 9, which is within the standard deviation bounds of Millard's plot. Finally, to summarize the key takeaways of our study, we found a weak correlation between muscle activation error and normalized tendon length. However, longer normalized tendon length had a strong correlation with a decrease in passive force. We see that this trend matches previous literature. And lastly, we note that muscles with small activation or forces were often outliers in these trends. To learn more from our study, it would be informative to compare both models against EMG data. This would allow us to make conclusions about how much better or worse compliant tendon modeling is, rather than simply being different from a rigid tendon model. Next, it would be interesting to observe the effect of compliant tendon dynamics for different gaits or loaded walking. And finally, for clinical application, it would be interesting to use the joint reaction analysis tool to compare how well the two models can predict improvement in internal joint forces for prescribing modified gait kinematics.
We'd like to thank Scott Delp and the entire teaching team for supporting us with this project. We'd also want to thank Scott Ulrich and Chris Dembia, people who were not involved in the class, but nonetheless were extremely helpful anyways. Thanks for watching.